Let's start. Actually, we had enough time for the quiz. I suppressed it because we were short on time, but we still lost those 10 minutes. And we have to finish on time because we have a faculty meeting just right after the class. Actually, you are busy. So I was telling the quiz was fun, but because it was 3 lectures and a lot of questions. So instead of that, let's go into the lecture, the second part of Timber. Just before that, just to remind you, I updated the notes on assignment 2, right? There was some data which was not correct. I said that the panels of this building were aluminum. They are steel. I checked the other day, right? And there are more comments, so you may want to look at it. I also uploaded the photos and the full list of the materials workshop we did, right? And if everything works okay, on Friday, after the questions and answers, the comments, and the midterm exam orientation, which is next Tuesday, we will have the second workshop, right? Mostly with the glass and timber materials. So I think you agree, timber is fascinating. You were all the weekend waiting for this lecture. We started by reviewing the 2 basic families of trees. They are called in many ways. They are not totally the same, but they are used in exchangeably. The conifers, gymnospermae, needle-leaved or softwood, and deciduous hardwood. Remember, softwood and hardwood are names. They are misleading. Don't know that. And we know that the conifers or softwoods grow faster. This means they are easier to exploit, and they are the ones used more often in construction. Doesn't mean that's the only we use. We said that the material is quite complex. We started from the composition cellulose, which is a long chain polymer. By the way, why a long chain polymer becomes stronger than a shorter polymer? Can you guess why? Say we have in reality it's a chain, right? So we have a chain. It is pulled. We say the chain breaks with the weakest of its points. But if we make the chain longer, right? Would it be stronger, the same, or weaker? What do you think? You don't think? We waited too much. Okay. You know, when you have to save somebody in a river and there's a human chain, right? And you have like 20 people and they can hold a lot of strength. We are very used to use the elasticity theories in which both will be the same because they have the same strength. But if we go to the energy theory, right? When it is pulling, the energy of the pulling is shared between all the points. So the longer the chain, the longer the greater is the energy they can accumulate, right? So that means a longer chain breaks much later. It's much stronger than a shorter chain, right? You can experiment with it. It's quite well known, right? This is the advantage of those long polymers. This is why the cellulose is so strong. So we say that the cellulose is those long fibers, those polymers. We have a shorter polymer, which is a hemicellulose. And finally, the lignin, which is another polymer, which creates the kind of rigid cover, right? So in a transversal section, we have the cellulose making like a microfibrils, like a big chain. The hemicellulose making a kind of elastic element in between, and the lignin creating a very tight, rigid package. And that's the basis of the fibers of the cells. So that creates a really, really strong structure in the tree. We saw this is organized in different ways depending on the trees. The softwoods have a very regular, very simple texture, have very clear ear rings, right? Whereas the hardwoods have much more complex texture. And if they are ring porous, we can see the ear rings, but not as defined line as it happens in the conifers. And we have a large amount of trees which actually do not show very clearly those year rings. We can see in the large picture, but it's not a clear defined line. So this is what allows us at least to distinguish between a softwood and a hardwood, right? Then the specific species, it takes practice to deal with them. And then we ended here. It was like the section of the trunk. So this is important, copy it, take the names, because you have to know where the trees sections are taken that will deal with the performance. And I checked all your activities, and almost half the class did it wrong, right? So the importance of drawing is to understanding things, right? And this is quite a simple, it's not simple, but it's not a very complex diagram. Many of you just looked at it and did something that you have invented, and that's a problem. So you have to take the names. So you have to process the radial section, tangential section, or horizontal transversal section, at least those three names, right? And know where is the cut within the cylinder, not just, and see the pattern, right? This is important. Where the ear rings, how we see them, right? Some of you draw them in the opposite or invented something. Those things are important. That this is why I tell you, insist so much, draw, right? Not only this. Whenever you draw something, you have really to be realistic, to see what you're doing. We draw to educate our eyes and to understand reality. Please be careful with it. And now we continue, right? We are still in lecture 10. So, and we have a very tricky language problem. This is happening only in English. So if we see the tree, right, we can see very clearly two zones in most trees. One very clear, which is the young wood, the one which is alive, right, which is called the sap wood. I put the Korean, yeah, Pyeongjae. It's easier to understand, much more logical. And the Hancha actually is the same as Chinese. So probably Chinese, I don't know how to read them, but maybe Fangjae or something like that. No idea. Japanese use a different word, funny one. So this is the alive part of the tree. And it has in all trees. You may count the rings is between 8-10 years, right? This is softer, is not structural, right? And this is what we call the sap wood or Pyeongjae. And the hard wood, in this case, is literal, yeah, Shimjae, is the part of the tree which is not longer alive. It is more rich in lignin, it's more massive, and this one which is more structural available, right? So those areas are important to know. Usually you will have not to deal with it because the makers, the factories will give you just the part which is necessary for your work. But it's nice, you know, it happens, right? And be careful because we have hardwood, softwood, hardwood, sapwood, and they are all different. So please don't confuse those words. Yeah, it's just pure linguistic, right? It doesn't happen in Korean, Japanese, Chinese, Spanish, probably French. English is as it is. So I took two photos. This is from Wikipedia, actually. One softwood. Actually, yew is very unique timber, very compact, one of the densest in softwoods. But you can see the difference, right? And the oak, you can see also the difference between the sap wood and the hardwood, right? This is not that this part cannot be used, but surely it will be twisting more and will be less reliable than the more lignified part. And this is one slide which is not in last lecture. I removed it. It confuses a lot, right? And I removed in the previous years, but some of you asked, how do trees grow? And that's the next question. We all know. Then why we ask, right? So if we have the transversal section, right? Well, if we see this section, we all will understand this is very old part of the tree. The top is younger, right? Because the trees grow upward. This is what creates confusion. So usually we'll use the lower part of the tree for construction. The rest is just lumber for burning, for biofuel or something like that. So in plant it's very easy to understand, right? We have a tree with several years, and the following year a new ring appears on the outside, right? And the following year another ring, right? And after a few years, those inner rings become lignified, right? And become the hardwood of the tree. But what happens in the longitudinal section? That's interesting, because trees grow like this, right? So the following year you will have kind of a subwood going up, right? And then eventually this subwood will become lignified, right? So this is the subwood, or pion, say, and this is the hardwood, right? Chim. But this is confusing. Stalin, this is the mature wood. This is the juvenile wood. Why is that, right? And I showed this because you asked, right? So the point is, the first 5 to 10 years in hardwoods, probably up to 15 years, the trees are very flexible, right? Because they are very weak, so they cannot be so rigid. So the wood, even if it lignifies, it becomes a part of hardwood, it's a different quality. And we call it a juvenile wood. And this can be 100 years old, right? But we call it juvenile. So this is a different part, which I will put in yellow, right? Yellow, right? It's a juvenile wood, which will be all the initial 5 to 15 rings of the tree. So we will have actually 3 areas: subwood, hardwood, and juvenile wood. And the quality is different. And this is what this picture is telling, right? So on the top of the tree, we'll have only juvenile wood and subwood because the tree didn't have time. Which means if we cut a tree with just 20 years of age, we may have not much useful timber, because we have 10 years or 8 years of subwood and then juvenile wood, right? This way, you have to grow trees, conifers at least 30 years, hardwoods 40, up to 100 years to have useful timber, right? I will not ask this in exam, but I think it was interesting. It's hard to grasp, it's confusing. But, and you will see it in very few places. Actually, you have to look hard to find this reference. I got it from the Japanese books. So I have the text, right? It's out. So for what I read, in hardwoods, it lasts less time. It's 5 to 10 years. Softwoods can go up to 15, depends very much on the species, the climate, and the circumstances, right? And usually in hardwoods, it will be a very small part of the tree, probably this thick, right? So you will not notice. In softwoods, since we use linear structures, the usual posts and beams, if you have this part, you have to consider it in the calculation. Again, it's not a big deal because the engineers already know or should know, right? And the commercial timber you buy, usually they take this part out, right? So this juvenile wood, when it dries, it twists because it has a much different structure. It's quite a different quality of timber. Okay. Interesting is the irregularities, and well, this is an old olive tree, right, which has a lot of irregularities. The first one are the knots. You know, again, if you are familiar with what we said before about the growth of the tree, those 3 areas, it will be not difficult to understand this. You know, trees when they are young, they have branches in the lower part. Then as they grow, these branches disappear, right? You have new branches on the top, right? So those branches disappearing are eventually covered by new rings, and they are embodied in the trunk, right? It's important to know that the branches grow from the core of the tree. And really, the root is in the center of the trunk, right? Always. So we can distinguish 3 areas. One in which the branches are alive, living knots. The grain changes, but it's compact timber, so we don't see the problem. There are places in which that branches were already dead when the tree is growing, and they're not fused together. This is like really having a hole, and we have to consider it. It's what we call the dead knots, right? And the oldest timber, of course, we take the sapwood out, right? Is the one who has no knots at all. This is the most valuable, the one we try to use for structures and the high quality construction, okay? So if you take the photo of the living knot, it's like the one on the left. The grain changes, so the performance of the timber will change, but it is continuous timber, right? However, that knot is as good as having a hole. So we have always to consider, especially in structural elements, and we'll try to avoid it as much as possible. Even for interior furniture, we don't want to have those holes in the timber, right? Or we have to glue them. And you see, sometimes the knots are appreciated because of the aspect, for giving a different character to the timber. This is again yew, Taxus, which is a timber which exists with varieties all over the world, right? And it's appreciated because of this very unique texture, right? Interesting thing, because this happens in a lot of trees, and this is important, and probably something related to this course in the exam next week, so please pay attention. I will go a bit slower here, because understanding how trees grow and how they perform helps you to understand the material a bit better, right? Then we have the catalogs of trees and materials. I will go faster because there's not mystery there. So all trees, conifers, and the broadleaves have what we call the belly, right? This could be a straight tree, and the back. The belly is looking at the sunshine. So all trees have a wider rings towards the sunshine and more compact towards the shaded area. If one tree is cut and you have a slice, you will know where is the south, right, or the north, because of the orientation of the rings. Provided there's enough sunshine, right? Some forests are so dense that the effect is not so strong, but that means the quality of the timber is the same, but obviously the area which is in the back is more compact, stronger, right? And we can take it into advantage when we make, for example, one beam, right? In beams, we have compressed areas and tractioned areas. So we'll try to have the most compact timber in the compressed area, for example. Whereas for columns, we'll try to have it more balanced and use the ones which are more symmetrical in general, right? This is different, so don't confuse. When trees grow in a slope, right, they are creating a small cantilever. And curiously, the conifers react in a different way as the broadleaves do. It's what we call the reaction wood. Reaction wood just lowers the quality of the timber, right? So we try to avoid it. This is why the forestry tries to work in horizontal land and with vertical trees. So conifers will develop a thicker, compressed area that we call compression wood, right? And it's very stiff. It is darker. It is very easy to appreciate. And you see the difference between the belly and the back we saw before. The quality of the timber is different. This will crack easily, will be very stiff because it needs to hold that compression. The same happens in the branches, okay? Only very big branches are used in construction, usually are lumber, but also if you have a cut branch, you can see what's the top and what's the bottom, right? Because of that reaction wood. The broadleaf react differently. They use like a traction wood. They increase the fibers. They are less lignite-sized, so they have more flexibility, but more those cellulose fibers to hold the tree. And also the color difference is not so big, but it's an area which is really hard to cut. It's like a anti-theft timber, right? It just messes, it's many fibers, so it's hard and it's hard to work, and we try to avoid also. This is what we call reaction wood. Again, I think it's interesting to know this because you can sit and know that the trees. In old days, architects had to go to the forest and choose the trees, cut them, and direct all that. Now we have all solved, right? So it's good thing you don't have to worry about this, but I think it's interesting you know about it. So this is an example. On the top is a compression wood in a conifer. See, very dark and very cracked, right? Whereas this is here in Sol, you see the heart of the trees here, so you can see the difference in growth. And it's not easy to appreciate, but you see the color is different. And the guys who felt, you see this very straight cut on one side, like trying in many ways the other side. You can see it was hard to cut this tree, right? So this is what I was commented. Right. So in both cases, there's a lower grade, and we'll try to avoid it in all cases. And then this is more interesting just for design. So as we said, the microscopic part of the tree has fibers in many directions, right? And that may reflect light in different way. And according to the cutting direction you choose, you may have a different visual effects, which are just for the visual effect for design, not for the thing, right? So trees like mahogany, sapele, many tropical trees, according as you look at them, they have like a brilliant and shaded areas. And the lower part is the fiddleback, which is produced by the reflection of the different directions of the fibers of the tree, right? You'll see this mostly in furniture or musical instruments and things like that. And that's what remained from lecture 10, right? With this, I think which is the most important. I hope this helps us to understand a bit more the trees and to see how complex but how interesting is the timber as a material. Okay. Now the full catalog, it's not full catalog, the full list of trees are in lecture 10. Here I showed only a few ones which I want to comment. You can read perfectly, right? The ones in orange is the ones you will see most often in construction. So pitch pine, I put it because it's the densest. So it is as dense, as hard as any hardwood, right? And this is about the most dense in conifers. Yeah. Remember, water is 1 ton, stone is 2.5, steel is almost 8, timber is 0.7. No wonder usually timber floats in water, right? And it's used for construction, but I don't see it so often around. The yew I add here, those trees can live for centuries and they're enormous. And also they have a very dense, very compact and very beautiful timber. Actually, this was used for the bows of for the weapons, right? Because they are so flexible. And this is why Romans try to make them disappear for the enemies not to make bows against them. Right? That's, I speak of Europe. It's very expensive and very hard to achieve, and it's mostly used in interior decoration. Still today, we use it for bows. Important thing, I put it here because this is very poisonous. The bark, the timber, the leaves, and not the fruit, but the seeds are very poisonous. If I go back to the Roman period, when the Romans were conquering Spain, the natives would carry seeds in their back to eat them if they were captured. So they would suicide with this tree. And we still, every year, there's some kind of a dead animal because eating the leaves and some kind of poisoned children. So it's not that you know it. Douglas fir, Oregon pine. I put it here because it's like the prototype of pine tree. And this is the one which is exported. So probably if you get American pine or American timber would be some of this family, right? And this is very stiff, very strong, quite durable, and it's used for structures, right? And you see the softness of the texture and the clarity of the ear rings, right? And now you know this section is, which section of the tree is this? Horizontal, radial, tangential? tangential, right? And this is the pattern, right? So this is up. This is why you have to draw it correctly, right? Because when we put a still wooden post, right? We have to put the top on the top, not the opposite, because timber is used to work in one direction, not the other, right? Scots pine, I bring here because this is the most common, Pinus sylvestris. I think that's a very close family to the Korean pine, the usual pine, right? You can see the resin vessels. Again, very clear late wood and very clear ear rings. I like really, really a sharp line, right? And curiously, Scotland was full of them, but Industrial Revolution shipbuilding just made it disappear. So you won't find those in Scotland. Now, hardwoods, we have plenty from tropical woods. I put in red because many of those woods are illegal or they're very protected, so it's very hard to see them. And the three in orange are the ones we use most, right? And of course, balsa, you are familiar with them. I put them more or less in density order, right? So I put just the densest in the beginning. Dalbergia africana is like Dalbergia is a full family you have in Brazil and in Southeast Asia. This African one is 1.2 tons per cubic meter. So it sinks in water. It's fantastic timber, very appreciated, right? And mostly illegally felled. Those trees need at least 80 years to 100 years to produce a timber we can use. Well, this is a photo from the samples we have for Friday. This is the horizontal cut, right? This is why we see all the vessels. You see that in all timbers, we can see many times the vessels on the naked eye, right? And this is a tropical timber. This way, it's so hard to see the rings, right? While thick tropical, but still we can appreciate in the deer rings. So beech is Nodobang Namu. That's Wikipedia. It has also varieties, European, American. It is fantastic wood, very reliable, very, very dense, right? It's about 700. See as the heaviest of the conifers, and very common. One, you see that you can appreciate the ear rings, right? But they are quite diffuse, right? And those bits you see are the rays, the transversal fibers which tie the vertical fibers, and this gives the aspect which is quite easy to recognize, right? This kind of soft ear rings with this kind of very characteristic, very regular rays in the texture. So this is American beech. Again, the rings are much more soft, much more diffuse than in the other places, and those rays are very regularly through the timber. Right. Ash, we saw the other day, again, is a very reliable, very strong tree. We use mostly for tools, things like that, but still you will see it in interior. And it's, again, it has very nice, very soft texture. But if you see it nearby, you will realize the complexity of the hardwoods, not the softwoods. And this is several photos. You see, it has some similarity with the oak we see later and with the beech we saw before, but it's a bit different, right? They have not so many rays, and you see the earrings are invisible. It's kind of you can guess them, but they're very, very diffuse. And oak, which probably is the king of the top of the hardwoods, right? This is American red oak. We have red and white. Well, there's many varieties, right? This is the photo I had. So red oak, there's like two main families, red and white. White is great for exterior, it's quite durable. Red is from drier areas, so they are used more interior for decorational purposes. And you see The rays of oak are also very, very characteristic. And this may mislead with beech, but you see the lines are longer and always not as ubiquitous in beech. More examples of the European, right? So you see there's a lot of variation even with the same species of tree, but those huge rays or those huge vessels, which can be seen by the eye, are very characteristics of oak. And of course, I have to mention balsa because it's the lightest and softest timber we have, right? You are very familiar with it, and it is called hardwood. Well, I have more samples from what we will see on Friday. So you have more familiars, and this is the radial cut, in which, again, with a very little magnification, you can see that tissue structure of the trees. And probably you're familiar with this place, right? And it has a tropical timber floor, but this is where being used to look at things with sharp eyes, not distracted eyes, lets you see a difference. The floor is a plastic imitation. The walls are natural timber veneer. This is a tropical timber. I cannot see which species, probably mahogany of this kind of family. I cannot say for sure. But when you see them side by side, it's so easy to recognize the fake. So please educate your eyes to recognize the materials by looking at them, right? So here the pattern is printed. The texture is pressed, but you see there is not much connection between the texture and the pattern. It's like a really fake thing. Actually, the pattern is not as strong in the real wood. So this is like a more oak texture with a tropical timber printing, which is quite weird result. So we have the first question, which was the question 4 of last week. We have a desk. I guess, oh, I forgot to take this out. So much better. So the desk, I think you are aware this is fake timber. So you can say first, it is softwood, hardwood. Or if your memory is good enough, could you remember if it relates to any of the species we saw in the examples before? And then, since we have not much time, I invite you before you leave to look at the walls, right, which are also fake timber, and also try to recognize which timber they're faking. If you remember, it's okay. If not. So at least you should be able to decide if this is softwood or hardwood imitation, right? But then the species is quite characteristic. So actually, it's the most popular imitation in Korea. Right. Okay, so who thought this is a softwood imitation? Okay, who thought it is hardwood? Okay, so about 50% didn't think anything. Okay, we'll see on Friday. So let's go to the boring part, which is the engineering of timber. Densities. You will see that hardwoods have a wider range. So you have tropical timbers that we saw, which are heavier than water, and some which are very light. But most, both hardwoods and softwoods, are in the same range of densities, right? Almost all timber we use are between 700 to 400, right? Both softwood and hardwood. So this is nice, you are familiar with that data. Then strength, this is a bit tricky. So please follow. Cellulose fibers are super strong, right? More than steel, just a pure fiber. For what is said, the molecules are really hard to break, those atom things. But timber is not pure cellulose, it's many more things, right? And the fibers are tied together, so the strength is much smaller. So usually humidity and temperature will change the strength. When we speak of strength of timber, we usually speak of 12% humidity in timber and 20% temperature. For instant load, instant is not that violent load, it's like the long, short-term load, right? Not long-term, like years or tens of years. So in real timber, we go to 1% from 10% to 1.5%. So we divide between 10 and maybe 50 or 60, right? So we consider pure timber like 1,000 megapascal, which is still close to low-grade steel strength. However, real timber is not the ideal timber. It has defects, it has the grain changes and so on. So usually we even reduce more. So in general, we use 50 to 20 megapascal or 500 to 100 kilograms per square centimeter. That's the safe calculation strength. Of course, you don't need to know exact numbers, but this is nice. You are able to compare with concrete, which is about this range, right? This is very good quality concrete and steel, right? And again, what we think is safe for the timber. Of course, it changes a lot because trees are very different, right? And the grade is different. But what's amazing is how strong is the fiber itself, and still how fairly strong is the final material. Remember that concrete is the same strength, but will be at least 5 times as heavy as timber, right? If we have long term, and long term is like many years, we have creep. In that case, we further reduce, right? Just half. Okay, that's the beams, and that's the final calculation, right? Especially in roofs. In columns, it's not so much a deal, but in roofs in which they are always in a very uncomfortable tension, that has to be taken into account. And this is the effect of creep in roofs, right? They don't break usually, just a big deformation. But if unattended, overloaded, if we have a big snow, maybe at some time it will collapse. That's the beauty of the tiles, which can adapt to that change of shape. The timber, which with time it reacts to the loads. Temperature is also important. So higher temperature makes the material softer. Think on plastics. This is in general polymer. And we consider like 1 degree reduces 1% of the strength. And the nominal data is for 20 degrees. In temperate climates, it's not a big deal. But my hometown, for example, reaches over 40 degrees in summer, 40 to 43. So that means like 20% reduction in strength, right? So we have to be aware of that. And the other thing is moisture, and then fatigue, moisture fatigue. You know, fatigue is when you have repeated cycles of load, unload, materials get softer. If the timber gets wet, and dry, it creates another fatigue. And we understand that the cellulose is hydrophilic, so if it gets wet, it loses strength. Yeah, we are used to do that, to know that. So this is a bit tricky. The saturation point is the point in which the fibers are totally wet, but you still have a space in the timber to get more water, right? So saturation, you have the fibers. So those fibers are full of water, but still the spaces, which we have plenty, are dry. This is what we call saturated. A saturation is where the timber is stronger. If you reduce the humidity from here, the timber becomes stronger. If it gets more water, it will not be weaker, right? The moment because the water in between spaces does not change, it's not structural anymore. So saturation point is the weakest point, right? And usually it's about 25 to 30% of total content of water of the timber. And we cannot dry totally, so 12% is the standard, right? But if you have it totally dry, it would be stronger. So that's the point. The weakest point is the saturated timber, right? 25, 30%, depending on the species. And then if it gets dry and getting humidity, it gets fatigued. So we have, again, to reduce the load quite significantly. So the strength stays there. This is just to give you an idea of the strength. Again, this is the perfect pieces. In real life, we take like a 25% or 10% of that value. You see that the tensile strength for standard moisture is quite strong. So speaking of a Newton square millimeter, this is a megapascal, right? This is very, very strong. Again, in reality, we reduce this very much. And softwoods are not much behind, right? So there's not a huge difference. Again, softwood naming is misleading. Codes, I took just example of the American code, but I'm sure Korean and Japanese codes have their own tables. Have the grades of the timbers by species, so you know which is adequate in terms of strength. And I will not explain this further. We can also pretty mention the timber related to the light. So small spans is 24th, largest spans is 1/15th, and middle spans is like 1/20th. You have a bit more detailed table here, depending on the things. You see the difference is not much big with the concrete or steel, because it's mostly a geometrical problem. And this tells also that timber is very efficient material in structure, right? So if you have very long span, for example, in concrete, with a big section, the weight of the concrete itself will be a big part, big percentage of the load. Doesn't happen in timber. Timber can be massive and still not add to the weight. So it's an added advantage in large spans, in big structures. And then timber shrinks and swells with environmental humidity. We see the ideal standard is 12%, but you know Korean summer, right? We have 100% in summer, but we have 30% in winter. And that moisture is absorbed by the timber swells, right? And you see tangential swelling. This is why you have to know what is the tangential. So we have the trunk, right? This is the race. So the swelling and shrinking is in the direction of the rings, right? These elements that shrink and swell. So in the radial direction, there is almost no difference. This is small, radial direction, but tangential can be enormous, right? And we have to be aware of that. And this is most common species, have a big swelling. So again, this is with the temperature. If we compare, for example, with the steel, right, or aluminum, the expansion, again, transversal is much farther. So it's like 3 to 7 times more than metals. Those organic materials have much more variation with temperature. Plastics, you have them here are even much more, right? Plastics have a crazy construction dilatations, but timber is something in between. And the transversal is always the one which works more, right? Parallel to the ring gears. So you always have to leave space for expansion, especially on the sides. So if the planks in a floor are like this, you'll need to have some additional space on the sides and a bit less on the top and the bottom, right? Because that will be a considerable expansion there. And with this, we go to the lecture 11, second part. Actually, it was impossible to finish this part in just 10 minutes we had. So let's see how far we can go. And for the exam, midterm exam, we can study only what we see today, right? Whatever is left, we will do in final exam. Which is quite a lot. So let's go fast into the processing. So from the tree to the timber elements we use, there's a process fabrication, right? The first thing we have to do is cut and then dry. And I go straight to drying. We'll see cutting later. This is what I told before of the water, right? So free water is the water which is between fibers, right? Which we dry very easily and doesn't affect to the strength. The saturation happens only in the fibers, right? And then we have the properly dried timber, which is about the 12 to 15%, right? And then super dry timber, which almost does not exist. Even if you dry it, it will absorb humidity from the atmosphere. So it's not way to do that. So saturation point, as we said, is 27, 30% is what you have the second image. And we can remove, in general, we try to go up about 12%, which you consider ideal, right? And as we said, completely dried wood happens only in laboratory. We can dry on the air, right? This is a Japanese timber place. So you have the planks with plenty of air going there. And you can go up to 16%, which is not bad, still in the range. But depending on timber, you have to wait 2 to 7 years. This is ideal, it's great, no energy, just waiting, right? If you are patient. So we are a bit more impatient. So we use kilns to dry the timber. And it can be just 1 week, but still it is up to 1 week spending fuel and energy. So this is where most of the energy of the timber embodied energy goes, right? And in this way, also hardwoods can go even to 3 weeks, right? So this way we can go to 12%. And the shrinkage is quite large. Again, radial shrinking can go 7% in oak, right? 9% in beech, so it's quite a big shrinkage. Radially, it shrinks also, but a bit less, right? But it shrinks mostly tangential in the right direction of the ear rings. Put that in your head. Visualize the ear rings shrinking and making all the pieces shrink commercially. And the most common are between 3–5% shrinkage. So what strategies would you have to deal with this? So if you have full logs, just the grooves will help to control that shrinkage and avoid cracks, unwanted cracks, right? Those are later cut in 4 or get in the heart in some way. So you have the cracks when you preview them, right? And you see the shrinkage is larger where the longer are those rings, right? Since the rings are circular, you have to visualize that kind of two-dimensional movement. There are other ways, like waiting it for being deformed and then cutting later, right? But if it is diagonal, obviously the shrinkage will happen mostly in the diagonal, which is where you have more, right? If you have parallel, will be almost parallel, right? Direction, because the amount of rings is more or less the same. So we have a plank for flooring. Depending on who you put, it will shrink on one way or another. This is one because most European books, this is what I was taught, you have to put the back to the bottom side and the heart to the top, so you will have not uncomfortable points in the floor, right? It will be kind of more regular. If I go to the Korean dictionary, they say just the opposite. So the way of doing is just letting the floor shrink like this. So you decide, right? The point is, one way or another, you have to be aware how this deforms, right? And this is where all this, my insisting on copying those cuts, identify them, knowing the grain, helps you to know how to use or how to put those planks, right? And to pre-visualize how they will shrink. If this is a timber storage, actually it's kind of a construction place. You see the cuts, but you can see the different deformation depending on the cut you have. So you may spend a while seeing here and see how those elements have a different change of shape depending on the cut. And this is taken from a Japanese book. Of course, you have three-dimensional moving also because the grain, the rays are not perfectly parallel, right? The tree has movement and has some kind of three-dimensional shrinkage or three-dimensional pattern, so it will affect. But you can see the logic of those shrinkages, right? This is with English. This is from the American standards. And you can see the logic of this shrinkage. So even though we are a bit short of time, since this is important, I invite you in this beautiful circle I put in the sheet, 1, 2, and 3, only those 3 cases, draw them, right? Draw the formation, and please copy carefully, right? Both the name and the pattern, but understand why this deformation happens, okay? So when we have it, not only in the exam, but in real life, it will be like a second nature. You will have much more intuition on how the timber will change of shape. Let's spend 1 minute with this. Only 1 minute. Actually, this one is very common. It's one of the trickiest, but for the exercise, just concentrate on those 3 cases. Okay, you have it. Don't worry if you couldn't finish, but I suggest you practice and you visualize it because it is very helpful. And timber makers or specialist carpenters are all their life just dealing with those patterns, right? So there's different strategies, waiting for it to shrink and then cut the excess, right? And this is what I tell you. So you have to leave even plank by plank, which is a strategy, space for expansion and always at the top of the bottom, right? But remember that the most extreme is transversal, right? Usually it's like 1 millimeter per 10 planks. If planks are 10 centimeters, right? You may have the idea. So probably 1 10-meter room will need like about 1 centimeter, about. So a very rough estimation of that stress space you need. So an example, probably you know the Mimesis Museum in Padua, Barosisa, which has a second floor is all timber, and it's quite big building. So in winter, it shrinks, and you can see the shrinkage there, right? Fortunately, probably this building was made in summer when the timber was thickest, right? And then just in winter, it shrinks. And this happens every 5 to 10 meters. If you go there, now in winter, you can see this opening, right? If you put the floor in winter, you have to preview it will swell later. This is a restaurant here in Seoul with a wooden floor, and you see what happens. They put the floor wall to wall. In summer, it swells and there's not space, so just bumps. I say, well, what has happened? It was perfect. In terms of solution, you have to cut and to remake again. And Hanna Square, this is a polymer, right? Polymers shrink in all directions and a lot. So probably it was perfect when they built it, but now it's a small disaster. So then we have the cut planning. I just added a few illustrations. It's a long catalog. I will not explain, just depending on the purpose and the traditions and the quality of the tree, we cut in different way. what the first thing we do is to take the sapwood out. It is used for pellets, for burning, or for veneering, for paper, things like that, right? Then there is, you don't need to memorize that, right? Each way of cutting has different advantages because of the different texture and the fibers and the use of the wood, right? And this endless way of cutting. Then you have the names. Again, you don't need to memorize it, but this is names and the denominations which change even in different regions in the same country, right? So it's like the Japanese system for cutting, different result, and different names you have there, right? Of course, sometimes very irregular trees like a U have a very unique texture. So the cut is just to have most of this kind of drawing, this kind of very unique texture in the cut, right? It's more for decoration purposes than structure purposes. And this from the American standards. And then other things which is interesting, since timber is still scarce, we cannot use solid timber always. So we have very thin layers of timber which are sliced. We paste in like, well, this is plastic, right? In chipboard or other kind of board, and we have a finishing like timber. And this is the same as the pencil sharpener, but large scale, right? And depending on how you cut, you have different patterns. So it's like examples of the patterns you can get with different ways of cutting and the names they have. Again, you don't need to memorize. And once you have the cut, this is interesting because if you do interior especially, you can design your own patterns on how you use these cut elements, right? And this is because you can play with it, have some kind of effect. This is some of the most common with their names. Again, you don't need to memorize, but you have this as kind of additional information. And then we go to the last part I want to explain here because it's important. The rest, the engineered timber is important, but it's mostly a catalog, right? And the environmental issues, as usual, we leave for after midterm. So problem with timber is coming from a living being, right? And on planet Earth, living beings are programmed for self-destruction. And that's playing against us. Doesn't happen with stone, for example, which also deteriorate with time, but not in the way trees do. So you have to deal with them. It's a famous shipwreck in Scotland, the Highlands, which is the timber dying but still giving life to new timber, which is quite a beautiful image. Probably this was a good quality oak, white oak ship. So we have 4 chapters. Let's go fast into them because we have to go as much as we can. Timber, once the tree dies, all biology feeds on it. So as it happens with us, when we die, we become food for other living beings. And that's what continues the cycle. There is a classification on how strong are trees to decay. And you'll see that some of them are really softwoods, right? Cedar, but as we said, white oak, redwood, which is kind of tropical timber. Many timbers are not here because they're not so much available commercially, but this is like the ones which we can use safely in the outside. Of course, we have Ipe, which is tropical, which was very popular here in Korea like 10 years ago. It's becoming a bit more expensive. Moderate is almost any other commercial tree, right? Douglas fir is the one we said the most common timber imported from America, and then almost everywhere else, like the normal pine, right? The everyday pine and so on. So the point is the wood will have what we call weathering. And it's not just water. The problem is mostly sunshine, right? The UV rays, which degrade the fibers and then they become gray. This gray color is typical of UV degradation. Usually, this is like a dust. You can actually move with your hand, but the tree under that is, or the timber under that is healthy yet. Usually depends on the trees, but we can say 1 millimeter every 20 years. So it's quite slow, right? You have a nice thickness and you need only to sand it, right? And to repair again. We have 5 minutes to the end. Thank you. So this is one example of one weathered and then repaired part. We have repaired logs of timber like 500 years old, right? And still, after 10 millimeters, the timber was perfectly healthy. This is a bench in which you see the part which has the sunshine is the one which is most damaged. Then we have molds and insects. We all love insects, right? So yeah, brown rot is very characteristic. It's like a cubic rotting, and you will see very often in outdoors timber furniture. White rot is more hidden in humid places, and they all just decompose the timber. Insects are nasty. Most annoying is the termites. It's very dangerous, and probably more annoying the wood bugs, right? They're different. Termites are very easy to deal with. This is the brown mold. You see a photo. This is here in Seoul. And this is a termite. Termites are tricky because they eat the core of the structure, so you cannot see them. And then the structure collapses without you knowing, right? They are very easy to kill. Most often you just inject the poison and they all die. I did once, and it worked, right? So usually when you are suspicious, the specialist will put kind of a sensor, and they will hear the activity. So by the sound, they can recognize, because there's not termites, there's a full set of families of species sitting there. So they will recognize the insect and they will propose the treatment. So this is, if it goes to this extreme, you have just to demolish, and this is wood only for burning. Wormwood is more tricky, because those guys are almost impossible to kill. They leave the eggs, and the eggs can stay there for years. And if you put some poison, you have to renew the poison every 15 days until they are burned and then they are killed. So possibilities are that you are killed before with that poison, before the insects. So the techniques to deal with this, especially in all furniture, in museums, frames, they have to deal with those worms, and it's quite hard. Usually they use like a total void and they just kill them, right? What we do, we use poison, right? We call it sanitized or treated wood, but it's wood with poison, so the insects will not be able to live there. Creosote is what they use in the kind of oil, right? It's embodied in the full timber, and this is what was used in the railway logs. And probably this is the treatment we have in the steps of Eginun Hill in the school, right? And if you are there, still after many years, the smell is terrible, so it's a bit polluting. Waterborne are the most common. So this greenish timber you will see often is copper. Copper is toxic, right? Chromium, arsenic, it's all poisons, right? Which is great, but this washes with rain and goes to the environment, and then you are contributing to add poisonous materials to the groundwater. And then the worst are the solvent type, which they have not only the poison, but also some kind of very toxic alcohol, which goes to the atmosphere and increases the pollution. So this is industry standard, but remember that whatever we do to the timber is adding poisons to them. Just not great. Important, because this is some question, is the reaction to fire. Timber burns, we know. But as it burns, it creates a coal layer on the outside. That's insulating. And that makes the fire to go slow down. This is why when we have a fireplace, thick logs last very long, right? They burn very slowly. And we can play with that in our favor. So we can calculate about one loss of 0.6 millimeter per minute. Again, this depends on the timber. Speaking of standard dense timber, right? You can simplify by 1 millimeter per minute, right? Which is much easier to memorize, it's safer. And just given that exercise, we know that if we add some exercise after 1 hour burning or 2 hours, we still have the section we need for the structure to be strong. So I wish to do like question 3, but we have 1 minute left, so please don't do it. Do it at home, because I will ask in the exam something like that. So please basic exam, everybody looks up. You love exams. It is in the handout. I didn't forget, it will be available at noon, right? So this is samples from experiments with structural timber, right? So after 3 hours, the loss of mass was not so big. And this demonstrates this specific wood could last, because this is for the high-rise building in Vancouver. We spoke last week. So an example, this is a project I finished 22 years ago. It was 1923. It has timber structure, again, fantastic, except for one we had to replace. It was like after 70 years, it was as good as new, right? And the rating was 1 hour because it's housing, but it had a fire. Firemen took 1 hour and a half to arrive, right? The local firemen had, it was summer, so they were in a traffic jam in the beach. The pump didn't work, so they called to the main firemen 60 kilometers away. They come, and after that, that burned. But fortunately, the disaster was not so big, right? The logs of the roof have to be changed, but the small concrete protection helps is not to go to the floors before. It is very sad to see your buildings burning. It's nice to see that the precautions you take to avoid the fire spreading kind of worked. Processed timber, I will not see it, you can read it. I will ask this all complete, not the sustainability. But we'll see only those two, right? Glulam and CLT, which is like the hot elements which you see in all constructions. Then it's nice you are familiar with the rest. But probably you heard the explanation is simple, and you don't need to think too much. So glued laminated, as you may guess, it's very hard to have a huge pieces for structural timber. So we just cut small pieces, right? Probably between 10 by 5, like the 2 by 4 of the Americans, and we glue them together. Then we have very good quality timber, and with this we produce big sections, and we can just combine the grain to have compensate shrinking. So we have a very much balanced, very good quality timber in huge sections. So glulam is what is used in most structural timber today, right? Of course, the joints are usually with steel, galvanized steel. And the Shigeru building already 8 years ago was making extensive use of this kind of glulam to have those big pieces, which otherwise would be impossible to find, right? And then cross-laminated timber, it's the same concept, but the fibers are rotated 90 degrees. That creates timber which is effective in all directions, right? On both directions, and is much more versatile. And this is the material which is used in most high-rise buildings we see today, and in some of the bridges and so on. Right, so you see CLT very often around, right? And at the smaller scale, we have the plywood, which is just a smaller layers, thinner layers of timber, again, crossing the grain to compensate for those contractions and those expansions, right? And with this, we will end today. So for the exam, those 3 kinds are quite important, so please be aware of them. It's not what you read the rest, you don't need me explaining you what is a chipboard and things like that. Sustainability, I want to comment, so we'll see after the midterm. Just if we are a bit bored, between midterm and the rest, we have assignment 6, sorry. This will count for the second half, will not be counting in midterm, right? And will be the same we do always, but with the timber, right? We'll submit, we'll speak about next Friday later. This is the usual, but related to timber. This is in the handout, it should be in Blackboard in 10 minutes, okay? So assignment 5, remember, have to submit on Friday, this Friday. And please, those who have the late assignments, which is quite a few of you, please submit. There's one more comment. Study, you can ask anything. Before you leave, please, on Friday, 28th, right? Which is session 9-1, is next week, Friday. It is the Koyon Games, right? And in the syllabus, I said clearly, as per school regulations, only those who actively participate in the games can have excuse for attendance. But last Friday afternoon, we got a note from the dean of the college telling, please let students go to the games. It says, please let go to them games. It's not, you have to let them, right? So I will put a poll on Blackboard to see who really wants to go to the games or not. And based on that, I will comment on Friday what we do this Friday, what we do next Friday, okay? So please be aware of that. That said, thank you again for